Bijaya Bikram Samal. I am a senior research scholar at Indian Institute of Technology, KHARAGPUR, India. And today I'll be speaking on 4D printing, experimental comparison between different programming strategies for FDM or FFF processed safe memory polymers. So this will be my outline today. So I'll start with the application landscape of 4D printing technology. I'll do some literature review starting from the very beginning to till now. And then I'll show some of our previous work that we did during my master's in 2016-18. And then I'll show some of my present work that I have been doing in IIT Kharagpur. And at the end, I'll show some of the working prototypes and conclude. So coming to the introduction, so what 4D printing exactly means? So 4D printing is a process of manufacturing a part layer by layer using a smart material. And once the part has been created, we can provide some external stimulus to it so that it can change its shape and size over time. So the fourth dimension here is time. So coming to the broad classification of 4D printing as per the literature that I have seen, that is, first one is the embedding of the smart material during printing. Second one is the printing of single smart material, its blend or its composite. And the third one is the printing multiple smart materials, its blend or its composite. So coming to the process of 4D printing, so the 4D printing starts with, first of all, selection of the right smart material as per the application areas. So after the selection of the right smart material, then again we have to choose the energy source. So here the energy source is the stimulus or passive energy source like heat, pressure, gravity, etc. So that depends on the smart material that we are choosing. And after that, we have to also see the precise positioning, which we generally say is the design for 4D printing. So here we have to design and have a proper arrangement of the smart material or the active component in a precise angle and position. So this is the application landscape starting from 2021 till 2025. We can see there are a lot of applications of 4D printing technology, starting from electronics and power, industrial space and healthcare, and consumer and appliances. So this is the literature review that I have shown in a roadmap from the very beginning. In 2013, Skylar Tibbets proposed the term 4D printing in a TED talk. And then after that, in 2014, he patented their technology and they created some morphing structures by combining two different materials. In 2014, Mizel and their group from Virginia Tech were the first to create actuated joints by combining safe memory alloy into the polymer during polyjet 3D printing. In 2016, Bodhagi and their group created self-expanding and self-shrinking structures by using two of the safe memory polymers having different glass transition temperature. In 2016, in India, we first started working on 4D printing, where we created safe memory alloy and safe memory polymer composite structure. In 2017, again, Bodhagi was the first one to provide the concept of programming during printing in FDM 3D printing process, where they studied the effect of extrusion temperature and extrusion speed also. In 2017, Jinsung Leng from HIT, they created two PLA-based safe memory polymer ink. The first one was a only polymer ink, which was able to reconfigure from 3D to 1D to 3D, and also 3D to 3D to 3D. And the second ink was based on the magnetite-based ink, which they used for remotely actuating of the self-expanding scaffolds. In 2018, Jack Zhou from Drexel University, their team studied the recovery of PLA-based safe memory polymer and its effect on thickness of the shape-changing behavior. And again, in 2018, Robertson and their group from University of Texas studied the recovery ratio, fixation ratio, and safe memory index of ABS and SCBS-based composites, where ABS is a hard structure and SCBS is used as a plasticizer. In 2019, KEJ Go from NUS, they studied the conductive PLA polymer. They used PLA polymer and they have created different electrical circuits. In 2020, Ye Li from Bradley University, they studied the kinetic evaluation for a cost-effective PLA TPU SMP, where they found out that the TPU PLA and TPU composition of around 80 to 20% weight was the best, that showed the best safe recovery. In 2021, recently, Mehrupia from University of Twente, they used PLA as a 4D printing material and created some structures, and they studied the effect of different process parameters on the safe morphing behavior. So coming to our previous work that we did in 2016-18. So we used 4D printing by embedding of the safe memory alloy during the printing. So here we first had chosen two designs. So first one was a 3D model of an origami, and the second one was a three-jaw gripper design. The first one, in the first one, we had chosen some of the parameters like chamfering gap of 1 mm and the structures in such a way that after morphing, it should become 90-degree perfectly. And the second one was used for grabbing something in the hot water. So to realize these designs, we had created the safe memory alloy and polymer structures, where we first of all took nickel titanium safe memory alloy, and we did the programming of the active component. So the programming procedure was, first of all, we have to bend the sheet, then in a precise angle that we want to achieve. Then after that, we have to fix it in a fixture. After that, we have to heat it at around 500 degrees Celsius for 15 minutes, and then we have to do the rapid quenching. And once that is done, we have programmed the active component. Now we can go for the embedding process. So the embedding process starts with, first of all, printing of the base. Then after that, we have to embed the safe memory alloy sheet during printing. Then after that, we can resume the printer. And on top of that, we can print. And so that we can, at the end, we can get a safe memory alloy, safe memory polymer composite, which we can use for actuation. So this is the hot water actuation test of the prototypes made that we can see it took around 22 seconds for the origami structure to become perfectly 90-degree, and the three-jaw gripper to grab something from the hot water. So this is my present work that I have been doing in IIT Kharagpur. So first of all, I am working on thermoresponsive safe memory polymer. So the mechanism of any thermoresponsive safe memory polymer is that we have two structures in the molecular level. The first one is the hard structures, or hard, we can say that is the net points within the polymer matrix, which are responsible for the thermal stability of the material during the deformation. And there are also long polymeric chain, which generally takes up the elastic energy, and they are helpful for recoiling of the safe memory polymer when an external stimulus is provided to it. So here we have two concepts that is coming up. The first one is the safe memory safe fixation and the safe recovery. So the safe fixation is the ability of the safe memory polymer to get fixed at a certain angle or certain deformation, which you generally can compare with the elastic rubber band. If we are stretching an elastic rubber band, we cannot fix it. So we cannot say that is a safe memory polymer. So for safe memory polymer, we have to have a safe fixation. And the safe recovery is the ability of the material to get recovered to the programmed state from the deformed state. So these are the programming strategies that is there in the FDM 3D printing process. The first one is the programming after printing. So generally this process starts with, first of all, we have the edge printed part, then we can take it in and put it in a fixture. We can make a fixture and put it there, and then after that we can, in that position, we have to heat it above the glass transient temperature of the safe memory material, and then after that we can quench it or cool it. So this programming cycle will be completed, and after that we can go for recovery. So we have to give it some temporary shape or deform it. Then after that we can heat it above the glass transient temperature and below the programming temperature, and after that we can get a recovery. The similar programming, what we generally do for any safe memory material as a post process, is getting done during the process of the FDM 3D printing, where we can see that we have the build platform onto which the hot polymeric material is getting deposited onto it. So this fixing part is getting done here because it is getting fixed to the build platform as per the CAD geometry, and this hitting part is also getting done simultaneously during the process. And once one layer has been deposited, we can deposit various layers on top of each other. And when we do that, the nozzle moves up and the lower layers generally cools. So this programming strategy is getting done here automatically. But we have to compare it experimentally that which one of them is giving us a better result. So which is the aim of my work. So for that, we have made a CAD model as per the length, breadth, and thickness. We have varied thickness too. So we have taken two set of samples. After that, we have used simplified 3D to slice it, and we have used FDM 3D printing to print it as per the default process parameters. Then after that, we have the final printed part, which can go for the testing, and the test setup that we have built here in our lab is a hot water actuation test, where we have a temperature controller and heater and stirrer, and along with that we take the video data and we use the open source video tracker software, and we calculate the angles, and then we can calculate the safe fixation, safe recovery, and safe memory index. And these are the fixtures that we have made so that we can deform it as well as we can use it for programming. So this is the angle measurement schema which we have developed so that this is a low cost characterization technique for for creating deployable structures. So here we can see that for the programming during printing, we have the part. So the part whatever we have built, that is the program state. So after that, we can bend it using the fixture by providing some preheat like 50° for 5 minutes. And once it is deformed in 90°, then again we can have some deformation error here, which also we are calculating and taking into consideration. And after that, once it is deformed, and we can keep it for some time in this state, and after that we can remove it from the fixture and we can take it to the testing bed, and we can use hot water to actuate it at around 70° Celsius, which is above the transition temperature. Here the material that we are using is a PLA, which has a glass transition of around 60° Celsius. So when we are providing it 70°, it will try to recover back. So the recover back angle that we are calculating is the theta end. And again, here also we have some fixation error, and all those things we are taking into consideration, and we're calculating using this formula. If we consider the case of programming after printing, then we have the as printed sample, which is as printed sample. After that, we are fixing it into the fixture, and in that state only, by fixing it along with the fixture, we are putting it in the hot water, and we are providing heat. That is, the programming heat is around 90° Celsius for 10 minutes that we are using it by doing the iterations. And once that is there, then we are removing it, and we are cooling it in room temperature water. And once that has been done, so we have reprogrammed, or we can say programmed after printing. So again, here also we are also considering deformation error. After that, we are again deforming it to 180°. Then from there, we are calculating whether it is reaching 90° or not. So these are the results, where we can see these are the results for programming during printing and programming after printing for set 1 and set 2. Set 1 is for thickness around 4 mm and set 2 is around 2 mm. So here we can see there is a comparison between the programming during printing and programming after printing, where we can see the programming during printing has provided us a recovery ratio of around 99.25%, very high. But we can see that programming after printing has provided around half, that is 55%. Similarly, the fixation is around somewhat good, but again, if we consider the safe memory index, which considers both the effect of safe recovery and safe fixation, we can see it is better for programming during printing than that of after printing. And if you consider for set 2 also, we see similar kind of result if we compare between programming during printing and programming after printing. And if we compare between the thickness, how the variation happens, then we can see that for the programming during printed part, when we are decreasing the thickness, the safe recovery decreases to a bit, but for programming after printing, we can see when we are decreasing the thickness, the programming increases, safe recovery increases, sorry. So here we have also done a cyclic failure test and life cycle assessment to find out how much cycle it can do the actuation. So for that, the best result that we had got is programming during printing for set 1. So we have taken one sample and we had done repeated tests. So it has performed well up to around 140 cycles, and with the decrement of safe recovery around 40%. So at the end, for 140, when we got after 140, when we got the failure, before that it was showing around 60% recovery. So this is the graph which shows how the functional characteristics of the safe recovery is decreasing with the number of cycles. So here we can see that when we are increasing the number of cycles, we are getting reduced safe recovery. So these are some of the working prototypes. So not only programming during printing showed better result, we can use it, but again, we can also use program after printing, so that to create such structures which are not possible by using FDM. And as we know that FDM is a low cost strategy to create 4D printed structures, along with PLA, which is the second highest used polymer with safe recovery. So we can use here we have used we have shown a 4D scaffold which we have printed. So we have the as printed structure. So this is already programmed during printing. When we are providing some stress, then it when we are hitting it, it recovers. So we can use this for minimal invasive scaffold deployment and for bone tissue engineering. And here we can see that we have a biomimetic flower where we wanted to create the motions that we see in flowers when it blooms. So generally, we cannot create such structures with FDM during printing. That is why we can use printing after programming after printing strategy to create such things. So here we can see in a video where we can see both of the strategies, and here this is a PAP, that is programming after printing. We can see we have programmed it to fold, and PDP, that is programmed during printing. So this has been printed straight. So of course it will try to become straight. So coming to the conclusion, we for the first time experimentally proved that FDM 3D printing method leads to programming and also shows improved behavior than data programmed after printing. And we can also use programming after printing for further intricate morphing of the shape memory polymer structure after printing. And in future works, we have also done some works that I have not shown here, that is changing some of the process parameters and design parameters so that we can control the shape morphing behavior. And in future work, we want to develop some novel hybrid nanocomposite of thermoplastic shape memory polymer for 4D printing applications in the areas of bone tissue engineering and photonics. And we also want to optimize the process parameters using meta-heuristic methods so that we can get a predictive shape recovery and better shape recovery. So I'm working on direct digital manufacturing lab IIT Kharagpur, which we have these facilities that I would like to show, that we have a metal additive manufacturing DMLS, that is direct metal ledger sintering US M290 with online monitoring and like melt-pool monitoring and optical tomography. And we have different scales, like we can go up to micro. We have the nanoscale photonic professional GT, that is a 2-photon polymerization process, where we can print up to feature size of few nanometers. We have Stratosphere Object 30, that is a polyjet printer, and we have a few Creality Ender series printers for FDM. And we have also converted one FDM to DIY recently, DIW. And for characterization, we have Tescan Lyra 3, which has a FESEM, EDS, electron beam lithography, and FIB. And we also have client deck micro manipulator, which is generally used for some micro robotic structures that we print using nanoscribe. So thank you for your kind attention. I would like to take any questions from here. And I would like to thank my Professor C.S. Kumar from Department of Mechanical Engineering and Professor S.K. Varshney from Electronics and Electrical Communication Engineering. And I'd like to thank my my co-author, Anita Jena from Advanced Technology Development Center. Thank you.